Welcome you in the lecture series of random processes detection and estimation. It is the 13th lecture of this series. In the previous lecture, we have discussed about Bayesian detector, base risk, ML detector, map detector, and minimax detector. In this lecture, we will discuss about multiple hypothesis testing and composite hypothesis testing. And the outline of this lecture are: we will discuss multiple hypothesis testing, then we will discuss composite hypothesis testing, and composite hypothesis testing involves two types of approach: Bayesian approach and the general likelihood ratio test. And in this lecture we will concentrate only on the Bayesian approach. And in the objective of this lecture, you will able to explain where the multiple hypothesis testing is used, and when the PDF of the hypothesis is not completely known, then how can you use the composite hypothesis testing to solve the problems. Now let us start with the multiple hypothesis testing. In many problems, we wish to decide one hypothesis from more than two hypotheses. That means M hypothesis where M greater than 2. These problems frequently occurs in a communication in which one of M signals must be detected, and also in pattern recognition system. To solve this problem, the minimum probability of error criteria or Bayes risk is commonly used. Let there are M hypotheses H1, H2 to Hm, and C and the cost Cij, the cost to decide Hi when Hj is true. Then the expected Bayes risk will be equal to R summation I 0 to m minus 1 j 0 to m minus 1 Cij, conditional probability Hi given Hj and probability of Hj. And for uniform cost assignment means C00 and C11 is equal to 0 and C01 equal to C10, it is equal to 1. And then the Bayes risk will be equal to the probability of error, and the decision region Ri will be the observed sample such that it decides Hi, where I is 0, 1 to m minus 1. Now the Bayes risk will be summation n I 0 to m minus 1 j 0 to m minus 1 Cij integration Ri probability x given Hi and probability of Hi dx. So from here you can write summation I 0 to m minus 1 integration in the region Ri summation j 0 to m minus 1 Cij, conditional probability x given Hi and probability of Hi dx. And you can also write this as summation I 0 to m minus 1 integration in region Ri summation j 0 to m minus 1 Cij and conditional probability Hj given x and Tx dx. This is from the Bayes rule. You can write this part as the conditional probability of Hj when x Px is given. And let this part summation j0 to m minus 1 Cij and conditional probability Phj given x, it will be equal to Cix, and this is the average cost in deciding Hi. And now the expected Bayes risk will be, that is R summation I 0 to m minus 1 integration in the region Ri Cix Px dx, and Cix is the average cost of deciding Hi. And as each x must be assigned to one and only one of the decision region Ri's, the cost contribution to R if to R1 is here the cost contribution to R1 is C1x Px dx, and the cost contribution to R2 is C2x Px dx, and so on. So we should choose the hypothesis that minimize CIX. CIX means here the summation J0 to m minus 1 Cij conditional probability Hj given x. So to determine the decision rule that minimize the probability of error, we use uniform cost, means Cix will be equal to summation J0 to m minus 1, where j not equal to I, and conditional probability P Hj given x, and I can write it as summation J0 to m minus 1 conditional probability P Hj given x minus P Hi given x. And here you can see this term is independent of I, so the cost Cix is minimized by maximizing this part P Hi given x. So the minimum PE decide Hk if the conditional probability P Hk given x greater than the conditional probability P Hi given x when I and k are not equal. So this is the M array maximum post priori probability map decision rule, and from the base rule I can write this condition as probability P conditional probability P x when Hk is given greater than the probability of x when Hi is given. Here I not equal to k, and this is correspond to the M array maximum likelihood decision rule. Consider one example. A ternary communication system transmit one of three amplitude signals 1, 2, 3 with equal probabilities. The independent received signal sample under each hypothesis are: under hypothesis H0, the received signal Yn is 1 plus omega n, and under hypothesis H1 the received signal is 2 plus omega n, and under hypothesis H0 the received signal is 3 plus omega naught, where n is 0, 1 to n minus 1, where omega n is the Gaussian distribution with mean 0, variance sigma square, and the cost are Cii is equal to 0 and Cij is equal to 1 for I not equal to j, where I and j are 1, 2 and 3. So determine the decision region and the minimum probability of error in this case. These three hypotheses, the PDF under in these three hypotheses are with mean 1. This is the PDF under hypothesis H0, and with mean 2, the PDF under hypothesis H1 is this, and with mean mu3, the PDF under hypothesis H2 is this. So these are the threshold value 1.5, 2.5. The prior probabilities are equal here. So pH0 is equal to pH1 is equal to pH2. It will be equal to 1 by 3 because they are equally likely. The ML decision rule applied here, and to minimize the probability of error, we should decide H0 if Y0 less than 1.5. So if this is in this region, we decide that H0 is true, and if we decide H1 if y is between 1.5 to 2.5, then we will decide the hypothesis H1 is true, and if y is greater than 2.5, then we will decide that H2 hypothesis H2 is true. So in this case, the conditional PDF can be written as conditional probability Py when Hi is given 1 by 2 pi sigma square is to the power n by 2 is to the power minus 1 by 2 sigma square summation n0 to n minus 1 yn minus ai whole square, where a a0 is equal to 1, a1 is equal to 2, and a3 is equal to 3. So this means for the hypothesis h0, the conditional PDF will be p y h0. It will be equal to 1 by under root 1 by 2 pi sigma square to the power n by 2 e to the power minus 1 by 2 sigma square summation n0 to n minus 1 yn minus 1 in the case of when it is under hypothesis h0, a1 is 1, and for the under the hypothesis h1, it will be probability y by h1, it will be equal to 1 by 2 pi sigma square is to the power n by 2 is to the power minus 1 by 2 sigma square summation n 0 to n minus 1 yn minus 2 in this case, because for the hypothesis h1 the value of ai will be 2, and for the under the hypothesis h3 it will be probability y h given h3 h2, it will be 1 by 2 pi sigma square to the power n by 2 is to the power minus 1 by 2 sigma square summation n0 to n minus 1 yn minus ai. Here ai will be 3, so in this case the value will be 3 here is to the power the whole square. So to minimize the this conditional probability, this conditional PDF, we can minimize this part. So this we will discuss about this part. Di square, consider this di square is summation n0 to n minus 1 yn minus ai whole square. So I can write this as summation n0 to n minus 1 yn minus y bar plus y bar minus ai. Here y bar is the mean of the observation yn, means y bar is 1 by n summation n0 to n minus 1 yn. So you can write it as summation n0 to n minus 1 yn minus y bar whole square plus n y bar minus ai whole square. And to minimize di square, we choose hi, for which ai closest to y bar. So you know the probability of error is equal to the 1 minus the probability of correct decision, and so you know the probability of correct decision will be summation from the base risk will be the summation I0 to 2 conditional probability hi, when hi is given probability of hi, this is for the correct decision. So in this case because all these the three prior probabilities are equally likely, means ph0, ph1 and ph2 are 1 by 3, so it probability of correct decision will be 1 by 3 summation I 0 to 2 conditional probability p hi given hi. So I can write it as 1 by 3 the probability y less than 1 by 2 y bar less than 1.5 when h0 is given, means we have decided the observed sample is less than 1.5 and we have decided given h0 is true, means we have taken the correct decision, plus probability when y bar is lie between 1.5 to 2.5 and h1 is true, this is also correct decision, and plus probability the sample mean y bar greater than 2.5 and h2 is true. So I can write it as 1 by 3 1 minus q 1.5 minus 1 upon under root sigma square by n, and it will be written as sigma 1.5 minus 2 under root sigma square plus n, and minus q 2.5 minus 2 upon under root sigma square by n, and this part it will be q 2.5 minus 3 upon under root sigma square by n. So this is the value of this part is this 1 minus q 1.5 minus 1 upon under root sigma square by n, and for this part these values are sigma this q 1.5 minus 2 divided by sigma square by under root sigma square by n minus q 2.5 minus 2 divided by under root sigma square by n. These are value for this and this value for q. 2.5 minus 3 divided by sigma square by n. So from here you can find out 1 by 3, 1 minus q, 0.5 divided by under root sigma square by n, plus q minus 0.5 under root sigma square by n, minus q 0.5 under root sigma square by n, plus q 0.5 divided by sigma square by n. And you know q minus x is equal to 1 minus qx. So from this you can have the probability of correct decision. It will be 1 by 3, 3 minus 4q 0.5 divided by under root sigma square by n. And the probability of correct decision is 1 by 3, 3 minus 4q 0.5 divided by under root sigma square by n. And I can also write this probability of correct decision. It will be 1 minus 4 by 3 q 0.5 by under root sigma square by n. And you know the probability of error will be 1 minus probability of correct decision. So from here the probability of error will be 1 by 3 q 0.5 divided by under root sigma square by n. This is the probability of error for this case. Now take another example. A ternary communication system transmits one of the three amplitude signals minus a, 0, a with equal probabilities. The independent received signal samples under each hypothesis are under hypothesis H0. The received signal sample is minus a plus omega n. Under hypothesis H1 the received signal is only the noise, there is no signal, and under hypothesis H2 the received signal will be a plus omega n. So under hypothesis H0 the signal is minus a plus omega n, under hypothesis H2 the signal is 1 plus omega n, and under hypothesis H1 there is no signal, only noise is there. So where omega n is the Gaussian PDF with mean 0 and variance sigma square, and the cost are Cii 0 and Cij is equal to 1, and for I not equal to j, and here I and j are 1, 2, 3. So the apply ML rule, maximum likelihood rule, and determine the decision reason and minimum probability of error. So in this case the three PDF under the hypothesis H0, H1 and H2 are, this is the PDF under hypothesis H0 with mean minus a, and this is the PDF under hypothesis H1 with mean 0, and PDF under hypothesis H2 with mean a. Because under hypothesis H1 there is no signal, only noise is present, and the mean of the noise is 0 and variance sigma square, and there are equal probabilities, equally likely probabilities, means probability of H0 will be equal to the probability of H1 will be equal to the probability of H2, and it is 1 by 3, they are equally likely. And to minimize PE, probability of error, we should decide X0, we should decide H0, the hypothesis H0, if the observed sample less than minus 1 by 2. So if the observed sample is less than minus 1 by 2, then we will decide H0, and if the observed sample lie between minus a by 2 to plus a by 2, then we will decide H1, and if the observed sample lie greater than 1 by 2, then we will decide the hypothesis H2. Now the conditional PDF in this case will be probability x given hi, it will be equal to 1 by 2 pi sigma square and not n by 2 e to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn minus ai whole square. Here ai means a0 minus 1, a1 0, and a2 is equal to 1. A2 is equal to a in this case. So to minimize this probability, we can minimize this part, and this part is di square, it is summation n0 to n minus 1 xn minus a whole square. and it will be summation n0 to n minus 1 xn minus x bar plus x bar minus ai whole square, and xi is the mean of the observation x, and this mean is 1 by n summation n0 to n minus 1 xn, and it will be, I can write di square summation n0 to n minus 1 xn minus x bar whole square plus n x bar minus ai whole square. And to minimize di square, we choose hi, for which ai closest to x bar. And you know the probability of error is 1 minus the probability of correct decision, and the probability of correct decision means from the base risk it will be summation I 0 to 2 conditional probability hi when hi 2 and the probability of hi, and this is 1 by 3 summation I 0 to 2 probability hi by hi, and it will be 1 by 3 probability the sample mean less than 1 by 2 minus 1 by 2 and given h naught is 2. So this is the correct decision, and the probability when x bar lies between minus a by 2 to a by 2, and the given we have given that h1 is 2, plus the probability sample mean greater than a by 2 given h2. So I can write it as 1 by 3 1 minus q minus a by 2 minus a upon under root sigma square plus n plus q minus a by 2 divided by under root sigma square plus n minus q a by 2 under root sigma square plus n plus q a by 2 minus a by under root sigma square by n. So this part will having the value 1 minus q minus a by 2 minus a divided by under root sigma square by n, and for this part you can calculate this value q minus a by 2 divided by sigma square by n minus q a by 2 divided by sigma under root sigma square by n, and the probability when sample mean greater than a by 2 given h naught, it will be q a by 2 minus a divided by under root sigma square by n. So I can write it as 1 by 3 3 minus 4q and a square upon 4 sigma square, and you know the probability of correct decision will be 1 by 3 3 minus 4q and a square by 4 sigma square, and I can write this probability of correct decision will be 1 minus 4 by 3q and a under root na square upon 4 sigma square. So now the probability of error will be 1 minus probability of correct decision, and it will be the probability of error will be 1 by 3q under root na square by 4 sigma square. Now we will discuss composite hypothesis testing. In simple hypothesis testing, we know the PDF of each hypothesis completely, but when we don't know completely the PDF of each hypothesis, then this class of testing is known as composite hypothesis testing. And so in this the PDF under h0 or under h1 or both hypotheses may not be completely specified. For example, if we wish to detect a DC level with an unknown amplitude A in white Gaussian noise, then the PDF under h1 means the probability of observed sample x0 when with unknown amplitude A and given h1 under hypothesis h1, it will be 1 by under root 2 pi sigma e to the power minus x0 minus a whole square by 2 sigma square, and a is unknown here. The PDF is not completely specified, so we cannot directly perform the likelihood ratio test here. There are two approaches to for this composite hypothesis testing. First is the Bayesian approach, and another is the generalized likelihood ratio test GLRT. In the Bayesian approach, the unknown parameter considered as the relation of the random variables as assigned a prior PDF to the hypothesis, and in the generalized likelihood ratio test, In this approach, the unknown parameters are first estimated and then use the likelihood ratio test. Now we will discuss Bayesian approach for composite hypothesis testing. In general problems, we decide between H0 and H1 when the PDFs depend on different sets of unknown parameters. These parameters may or may not be same under each hypothesis. Under H0, assume that the vector parameters theta naught that belongs to phi naught is unknown, while under H1, hypothesis H1, we assume the vector parameters theta 1 that is belongs to phi 1 is unknown. The Bayesian approach assigns prior PDFs to theta naught and theta 1, that is p theta naught and p theta 1. So in this case, the PDF under hypothesis H0 will be integration of the conditional PDF x by h theta naught, and H0 is given, and the probability of theta naught, the prior probabilities we have given to the unknown parameters, and the conditional probability under hypothesis H1, it will be the integration px by theta 1 when H1 is given, and the probability of theta 1 d theta 1. The unconditional PDFs px H0, px H1 are now completely specified, and they now not depend on the unknown parameters here. And with the Bayesian approach, the optimal NP detector decided H1 or H0 if the PDFs, the ratio of the PDF under hypothesis H1 and under hypothesis H0 will be greater than or less than with threshold value. So it will be equal to integration p x by theta 1 when H1 is given, and probability of theta 1 d theta 1 divided by integration the conditional PDF x by theta naught h theta naught and probability of theta naught d theta naught. The required integrations are multidimensional with dimension equal to the unknown parameters. The choice of prior PDFs can also be proved to be difficult. If indeed some prior knowledge is available, then it should be used. If not, we can have the PDFs as flat as possible, for example uniform distribution. Now we'll take another example. We have two hypotheses with unknown DC level in white Gaussian noise. Means under hypothesis H1, the observed sample xn is omega n, because in the under hypothesis H0 there is only noise, and under hypothesis H1 the observed sample xn will be a plus omega n, means DC level under noise omega n, and where DC level a is unknown and lies between minus infinity to infinity, and omega n is the white Gaussian noise with mean 0 and variance sigma square. Now we solve this problem by using Bayesian approach. Let A having the normal distribution with mean 0 and variance sigma a square. Now the conditional PDF under H1, it will be probability x by a when the parameter a is here, and with H1 is given under hypothesis H1, it will be 1 by 2 pi is to the power n by 2 into 1 by sigma is to the power n is to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn minus a whole square. The PDF under H0 is completely known because under H0, under hypothesis H0, there is no signal, only noise is present, and you know the PDF of the noise is a white Gaussian noise with mean 0 and variance 1. So the simple NP tester decide H1 or H0 if the Px H1 by Px H0 means integration minus infinity to infinity Px by a when H1 is given, and probability of a dA divided by the PDF under hypothesis H0 means Px H0 will be greater than or less than threshold value gamma. So from here, first we will calculate the PDF under hypothesis H1. So the PDF under hypothesis H1, it is minus infinity to infinity. Conditional PDF x by a, when H1 is given PA, probability of A and DA, and it will be the probability under hypothesis H1, it will be 1 by 2 pi to the power n by 2 into 1 by sigma to the power n e to the power minus 1 by 2 sigma square summation n0 to n minus 1 xn minus a whole square, and PA, probability of A, and we have assumed that A is Gaussian random variable with mean 0 and variance sigma a square. So it will be the PDF of this PA will be 1 by 2 pi under 2 pi sigma a e to the power minus a square by 2 sigma square dA, and after integration you will get here minus integration minus infinity to infinity 1 by 2 pi is to the power n plus 1 by 2 and 1 by sigma is to the power n and sigma a, and e is to the power minus 1 by 2 1 by sigma square summation n0 to n minus 1 xn minus a whole square plus a square by sigma a square, and integration with respect to dA, and let this is QA. So first we will find this QA. The QA is here 1 by sigma square summation n0 to n minus 1 xn minus a whole square plus a square by sigma square. So it will be equal to 1 by sigma square summation n0 to n minus 1 x square n minus 2n by sigma square x bar sample mean into a plus n by sigma square a square plus sigma square by sigma a square. The sample mean, it is 1 by n summation n0 to n minus 1 xn is the sample mean. So now you can write it as n by sigma square plus 1 by sigma a square into a square minus 2n by sigma square sample mean x bar plus a plus 1 by sigma square summation n0 to n minus 1 x square n, and this part is equal to sigma a by x square. The conditional variance is the conditional variance, and minus 2n conditional variance sigma a by n square sample mean x bar a divided by sigma square and the conditional variance sigma a by x square plus 1 by sigma square summation n0 to n minus 1 x square n. So from here you can have 1 by sigma a by x square into a minus n x bar sigma a by x square by sigma square and whole square of this value into n square x bar square by sigma to the power 4 and sigma a by x square plus 1 by sigma square summation n0 to n minus 1 x square n. So from this you can have the ratio of the PDF under hypothesis H1 and under hypothesis H0. It will be 1 by 2 pi to the power n plus 1 by 2, 1 by sigma is to the power n sigma a, and this is integration minus infinity to infinity e to the power minus 1 by 2 QA, and from the previous part you have calculated the QA is this value, is the QA. So from here, and the PDF under hypothesis H0, it will be the noise. It will be the noise under hypothesis H0. So it will be the PDF of this will be 1 by 2 pi to the power n by 2 into 1 by sigma to the power n e to the power minus 1 by 2 sigma square summation n0 to n minus 1 x square n. And with the NP test, this likelihood ratio will be less than or greater than some threshold value gamma. So if this likelihood ratio is greater than gamma, some threshold value, then we will decide H1, and if this is less than threshold value, then we will decide H0. So taking natural log both sides, you will get the x bar whole square greater than less than gamma dash, and or you can write as mod of x bar greater than less than gamma dash, as the unknown DC level can either be positive or negative. The detector is performed by comparing either the square or the absolute value of the sufficient statistic with an appropriate threshold. So the sufficient, this is the sufficient statistics x bar, you know, it is 1 by n summation n 0 to n minus 1 x n. So we compare the mode of this or square of this sufficient statistic with the threshold in this type of decision problem. So far in this lecture we have discussed about multiple hypothesis testing, composite hypothesis testing, and this was the 13th lecture of the lecture series of random processes detection and estimation. In the next lecture we will discuss about the composite hypothesis testing, where we will discuss generalized likelihood ratio test for composite hypothesis testing. And other than this, we will discuss local optimum test and detector comparison technique, and also we will discuss about asymptotic relative efficiency. Till then, thanks for listening this lecture. Thank you.